This video is intended to be an introduction to magnetism. You probably already know a lot about magnetism. I suspect you've been playing with magnets since you were a little kid, and you probably know very well that sometimes magnets can attract each other, but other times they can repel each other quite well. You've probably also noticed that magnets are capable of sticking to some things, materials we call magnetic, but not other things. So, what's the difference? That's what this video is going to attempt to explain, and to really talk about what the origins of magnetism are. And we're going to introduce a new concept called the magnetic field. Just like we saw masses alter the space around them and create gravitational fields, charges alter the space around them and create electric fields, magnetic poles alter the space around them and create magnetic fields. But I want to see if we can find some patterns of the magnetic field here. So the way this is done, I had you draw a magnet on the paper, I had you put the magnet on it, and we could see from the compass that the red needle, which is the north pole of the compass, is pointing away from the north on this magnet. So what I asked students to do was to make maps by marking that red arrow and then moving the compass out and repeating the process. And basically you follow the line wherever it goes. And now we're going back into the magnet at the south. So we could trace out a line, and we use the direction of the red arrow to draw arrows because magnetic fields have direction. And we could see that they go out of the north and then back into the south. Here's the complete field for one magnet. There's one limitation in this picture, which is that it limits us to mapping the field in the plane of the paper. If we could move the compass all around in 3 dimensions, we would actually see something much prettier. So this is a 3-dimensional view of that same thing. This is a box filled with oil, and there's some iron filings in it. And you can see those iron filings act as tiny magnetic compasses, and they line up all around the poles. So what we're seeing here is really just a slice right down the middle of that. So we see what it looks like in 2 dimensions. These field lines all appear to be loops. So it's pretty obvious for these guys out of the north into the south. But I think it's also pretty easy to see that this guy goes off the page and is continued by this guy. And basically all of these are loops. Interestingly enough, if we could break the magnet in half, what we would see is that they are entirely closed loops. That if we could go inside the magnet, we would see that they continue back like this, moving in the opposite direction inside the magnet. We'd also see something that maybe isn't super apparent. I didn't draw that so well. These lines never cross each other. So they're very intense here in the middle of the magnet, but they're never actually crossing, although that's hard to see. So that's pretty interesting that a magnet creates a closed loop of magnetic field. And the fact that these field lines are here in the magnet also tells us something really interesting. If we suddenly broke this magnet, we would see that the lines are moving back in this direction. And what that means is the lines are going into this broken part of the magnet here. Well, where do lines go into a magnet? At the South Pole. So what we've essentially done is made a new South Pole and a new North Pole. That's one really interesting thing about magnets. Until very, very recently, no one had ever isolated a single pole, and that's still only been done under very exotic conditions in the lab. There are no naturally occurring single poles. Every time you make a new South Pole, it seems like you make a new North Pole too. And you can see that idea of the field lines going out of a North Pole and into a South it doesn't really discriminate on which north or south pole. These field lines are going from this north pole to this south pole. These field lines are going from this north pole to the south pole over here. That showed a situation where there was a north pole facing a south pole. Let's look at what happens when you have two like poles facing each other. All of this jumbling up here in the middle has to do with the fact that magnetic field lines do not cross each other. So as the compass was in the middle here, there was a very rapid switch from the needle pointing this way to the needle pointing 180 degrees. So we've got this jumbled place where the field lines essentially crash into each other and move outward perpendicularly. So we can describe the shape of magnetic fields a little bit better now. It's time to talk about why they exist. What makes certain materials magnetic and other ones not? The scientist who really gave us the clues as to what was going on was a Danish scientist named Hans Christian Orsted. Let's look at the experiment that showed him what the cause of magnetic fields is. We have our battery, 9 volts. We have a loop of wire that runs up, over, down, and right now it's not hooked up. The positive is connected, but there's no connection at the negative. So the circuit is open and no current is flowing. Watch what happens when I hook up the negative. Compass needle experiences a deflection, and it goes back when I disconnect it. Now that was a subtle effect, but he knew that this was something important, that this was a link between magnetism and electricity that had never been discovered. So what we now call Orsted's law basically says that what creates a magnetic field? An electric current, moving charge. And that's become really the basis for our understanding of magnetism and electricity. That raises some questions. As Professor Bitter in one of the videos you're going to watch pretty soon points out, what are the electric currents in this magnet? It's got to be something moving around inside the atoms. And electrons are easy to single out since we know they're the things that buzz around the outside of atoms. But that raises a question. Sure, this is made of atoms with electrons, and this coffee can is too. So it makes sense the coffee can would experience a magnetic force. But isn't this textbook made of atoms? No magnetism. This copper tube is made with atoms. No magnetism. No magnetism from ceramic, or asbestos, or chalk. So what is it about this magnet and this can that allow them to be magnetic? Well, if we're going to go back to Orsted's law and say it has to be because of moving charges, let's take a look at the electrons. It turns out that electrons themselves are actually tiny little magnets. Now, exactly how the electron is a tiny little magnet is way beyond the scope of this course. To really understand it, you need the type of science known as quantum mechanics. But if we think of the electron as being a magnet, it's got a north and south pole. And just like a little magnet whose south pole was pointing this way would behave differently than one whose north pole is pointing this way, electrons can behave differently too. And it turns out this idea of electrons with their poles oriented differently, it turns out that that's really helpful for understanding how electrons behave in an atom. We're going to see that there's two types of electrons we have to look at, and they essentially correspond to having their poles in different directions. This is called electron spin, and don't get too hung up on the directions I've got here. Just know that some electrons have their poles pointing in one direction and others have it pointing in the other. Chemists usually call this spin up and spin down electrons. What would happen if we had two magnets right next to each other? And we'll say that this one has north here and south here, and we'll put the other one opposite above it. A lot of their magnetic field would be canceled out by each other. So If you happen to have two electrons that are close together, and they're spinning in the opposite direction, in other words, their poles are pointing different ways, we expect their magnetism to not contribute that much. So as we go through and think about where electrons are in the atom, that's going to help us understand whether the magnetism from each electron is visible or whether it's canceled out by a nearby electron. I suspect most of you guys remember filling in electrons into orbitals and remembering that the first orbital in an atom can hold 2 electrons and that the next one has room for 8. Actually, that second one is not just one orbital. It's actually 4 orbitals that are closely related in energy, and each of them can hold 2. The reason you can hold 2 is that you have room for one that has one type of magnetism with its north pole pointing one way, and one with the other type of magnetism. We're not going to go into the details of this, but if you're curious, I'll provide a link if you've got the chemistry background and would like to learn more. What we'll find out is that overall, an atom can be magnetic if all of its electrons don't cancel each other out. So the zinc atom does not show strong magnetic properties because all of its electrons end up paired. The magnetism of one electron cancels out the magnetism of another. That does not happen for either copper or iron. There's a lot of complicated reasons for why copper doesn't appear to be magnetic, even though it does have an unpaired electron. But what they boil down to is we see a single copper atom should have an unpaired electron. But we didn't look at a single copper atom, we looked at a piece of copper metal. So how is that atom responding to the atoms around it? Where are their electrons? All of that's important. So copper does not appear to be magnetic, even though a single atom does have an unpaired electron. What we really need to do to see bulk magnetism is we need to find a way where atoms reinforce each other's magnetism. And that happens in a certain kind of material called ferromagnetic materials. And iron is a great example of one of those. This thing sticks to steel stuff. It's a pretty strong magnet. My coffee can doesn't. But they're both made of iron. So what's the deal? What makes this magnetized and that not? Well, like I said, iron has these little domains, these little regions, where neighboring atoms reinforce each other's magnetism instead of canceling. But those domains are still very small spaces in iron material. So even though everybody here may all have their north poles pointing in one direction, next door it's going to be different. And next door it's going to be different. And everybody's going to be in a random direction. Because all the domains are pointed in random directions, this piece of iron or steel doesn't appear to be a magnet. And that's consistent with a lot of the iron or steel we see in our lives. But this can be magnetized. And the way you do it is to put a strong external magnetic field, which I've got labeled B here. You'll notice that some of these domains are lined up with the field and others are not. Let's see what happens when you do this. These are 2 not very impressive bar magnets. You could see from this oil and iron filing mix I've got on top of them that they're barely making the iron filings line up along their magnetic field lines. But that's pretty easy to fix. All we have to do to magnetize them is put them in the presence of a strong magnetic field. So what we're going to do is we're going to take our magnets. We'll put the south in like that. We'll put the north in like this. We'll put just a piece of metal over it, turn it on, give it a press, and now we'll check. As you can see, there's a fairly strong magnetic field, and these magnets will once again be useful objects. what happened? Well, the bar magnets originally were like this picture. Their domains were pretty randomly arranged. But some of those domains were aligned with the field, some were against it or not on the field. And as time passed in the strong external magnetic field, it was energetically favorable for atoms to switch from being in this domain to being in one aligned with the field. So in other words, this domain grows at the expense of these two. And we get something like this. At the end of the day, we're left with lots of atoms and lots of domains pointing in the direction of the external field. So we've now magnetized that piece of iron. It will behave as a magnet. Once Orsted had discovered that moving charges, electric currents, are the cause of magnetic fields, the race was on to see if there was any other relationships, particularly the inverse relationship. Is there some way magnetism can cause electricity? And the two people that get credit for finding this are a British scientist named Michael Faraday and an American scientist named Joseph Henry. This was the early 19th century. And what they discovered is, yes, you can make electric current using magnets. So what I've got here is a coil of wire, and they are hooked up to a meter called a galvanometer. And it's measuring current in microamps. So this is pretty small amounts of current. I'm going to flip my coil up so it's easier to see what's going on. And I'm going to pick up the magnet and I'm going to put it inside the coil. And I want you to watch what happens. So I don't know if you saw that, but the needle deflected to the left towards negative currents. And now that I'm leaving it in here, it's not doing anything. If I pull it out, it deflects towards the right, towards positive currents. And then it stabilizes. So that was interesting. They had found out that magnets can cause electric currents. The magnet has to be moving. So this became the opposite of what Orsted had discovered. Orsted says moving charge can cause magnetism. Faraday and Henry say moving magnets can cause current. So as I stick this in and out, I'm making the alternating current electricity back and forth. And I want to try to figure out why. One thing I hope you can see, and I'll replace this magnet with a picture I've made, is that as I move the magnet in and out of the coil, I'm changing the amount of magnetic field inside. Obviously, I can't put this in, but you can see at the pole, the magnetic field is the strongest, where the lines are closest together. So as I move that pole up and down, the amount of magnetic field enclosed by the coil is changing. And that seems to be one of the things that makes the electricity more and more. So what we have to do is define this idea of magnetic field inside a little better. There's a better word for it, which is called magnetic flux. So magnetic flux, which is symbolized by the capital letter phi, is the amount of magnetic field passing through an area. We're going to see it depends on how strong the magnetic field is, which is symbolized by B, how large the area of the coil is, the cross-sectional area, and then what angle the coil is at. I think it's obvious that the stronger the magnetic field, the more magnetic field you'd have inside the coil. I think it's important to look at these other two variables. It can be hard to show magnetic fields sometimes because we're talking about things that are acting in 3 dimensions. So here's a coil from the side, and you can see it's wrapping around this magnetic field. And the way we show arrows coming out of something, we use this little symbol here, which is supposed to be like the head of an arrow. So in this case, we've got as much magnetic field going through the coil as we possibly can. If we made the loop of wire in the coil bigger, we would enclose more of these lines and we'd have more area inside. So that's why area matters too. The other thing we can do though is we can rotate the coil. And if we rotate the coil like this, there's less lines that fit through because the coil is no longer perpendicular to the lines. So it's almost like we've closed off some of them. So that has changed the flux, just rotating it. In fact, if we rotated the coil completely parallel, we would have no flux at all. So that's why rotating it matters too. So changing any of those three variables, field strength, area, or angle, is going to change the magnetic flux. So what Faraday started to figure out was that changing flux was responsible for producing parent potential differences, which we call EMFs, and therefore currents. Let's change the flux at different speeds. Obviously, I can't really change the strength of the magnetic field. I've got one magnet. I can't change the area of the coil. But what I can do is I can move the magnet in and out faster. When I go relatively slow, notice that I don't get large currents. But when I move faster, I get larger and larger currents. The equation known as Faraday's law is what really sums this up. If you look here, we have a delta phi over delta t. That's a speed, the speed at which I change the flux. I can change the flux by either increasing the magnetic field, which is what I did by sticking the magnet in. I could also change it by changing the area of the coil, or by rotating the coil. But the faster I do that, the more EMF, or voltage difference, and therefore current I'm going to make. So we expect to see the needle move more. Let's see if we can do a delta phi over delta t by changing the angle the coil is at. So I have a compass, and it shows that north, the Earth's magnetic field appears to be pointing away from the camera. And that means there's magnetic field lines passing through this loop. In other words, its magnetic flux at the moment due to the Earth's magnetic field is as large as possible. If I rotate it, now there's no flux because basically field lines that are pointing away from the camera can't pass through it anymore. But now it's at a maximum again. If I do this quickly enough, I should be able to see a current produced. Most of you know that one of the major ways that we transport energy is through electricity. And we've talked about a huge number of sources of electricity so far this year. Most of these energy sources are turned into electricity the same way. This is the basis for how we generate electricity. We're going to see that it's going to convert the mechanical energy I put into it into electric current, which is what all generators do. There's a few basic parts to it. There's obviously the crank. There's a magnet. Most important part, though, are these coils that can spin. And notice they spin between the poles of the magnet. We've talked about the idea of magnetic flux, and that's how much of the magnetic field is in the coils. And I think you could see when the coils are like this, the maximum amount of magnetic field can get through, because you can see the inside of the coil, kind of the donut hole. When it's like this, the minimum amount can get through because that donut hole's facing away from the magnetic poles. So I'm going to keep cranking always in the same direction. But watch the galvanometer. Something really interesting happens. It's alternating. It goes back, forth, back, forth. But I'm still cranking in the same direction. So what I'm making is an alternating current. It's just worth noting that that kind of alternating current is very different than the direct current we get out of a battery, where we say positive charges leave the positive and always flow towards the negative. So there's two very different types of electricity you use in your life. The direct current that comes out of batteries that always flows in one direction, and the alternating current that comes out of generators and moves back and forth.